I guess we can start, right, Dr. Nick?
Okay. Okay, please.
Okay, very good afternoon to my dear lecturers, Dr. Haslinda and also Dr. Nick, for evaluating our presentation. So today I, Rashwinder Singh, will start up with the presentation. So there'll be project overview, following by waste treatment, followed by cost estimation, and the presentation will be ended with individual equipment design. Without further ado, let's move on to the project overview. So one of the most important thing in the previous plant design project was the separation system. So as you can be seen here, one of the important equipments were the vertical two-phase separator, where it works to separate liquid and gas. Another important equipment in the separation system was the distillation column, where it separates methane, ethane, and propane. And this will be further explained in detail in the equipment design. Now moving on to the next slide, I would like to pass it to my teammate Izzat.
Okay, moving on to the process flow diagram. This is our plan for the FLNG. So we start with a horizontal separator, and then goes to a mercury removal unit, and then a acid gas removal unit, and then it goes to a dehydration unit, and after that it goes to a demetanizer, and last but not least it goes to the liquefaction unit, which to liquefy the natural gas. And then next it goes to the basic control strategy. So for the horizontal separator, we control the flow rate of the inlet gas, and then we by manipulating the flow rate of the inlet stream. We also maintain the pressure inside the separator by manipulating the flow rate of the gas outlet stream. So for the absorber column, we control the composition of absorbed CO2 at the outlet gas stream by manipulating the liquid solvent flow rate. We also maintain the liquid level inside the absorber by controlling the manipulating the flow rate of the liquid outlet stream. Next, for the distillation column for the demetanizer, we control the composition of absorbed methane at the outlet gas stream by manipulating the reflux ratio of the distillation column. We also control the flow rate of the inlet feed by manipulating the flow rate of the inlet stream. We also maintain the vapor pressure inside the column by controlling manipulating the flow rate of the steam inlet stream of condenser. We also maintain the liquid level of the column by manipulating the flow rate of the bottom outlet stream. And last but not least, control the temperature of the column by manipulating the flow rate of the steam inlet stream of reboiler. And then this is our P&ID diagram. So I pass to the next person, Jasmine. Dash.
Is Rashwin there?
Sorry, my microphone was muted. As you can be seen here, the first one is the separator, then the adsorption column, then the mercury removal unit, then the moleculars. This is the water removal system, and then this is the demethanizer, and then this is the liquefaction system. Now I'll move on to the hazard and operability studies, which was also done for the previous project, where the three main study notes was the two-phase separator, the distillation column, and also for the adsorption column. As it can be seen here, this is the sample of the HAZOP.
Why does the slide is not moving?
No, it's moving.
Well, I see.
Rash, you
Rash is not
take
moving.
control.
Take control first.
No, I already take control. Is it moving?
Yeah.
Sorry guys, I think it's lagging. Is it okay?
Yes, it is. Yes, it
Okay,
is.
I'll continue. So moving on, this is the side view of the FLNG plant, and then there is also the top view. Now, with that, I would like to pass it to the next presenter to present waste treatment.
Jasmine?
Jasmine,
are you muted?
you mute the mic.
Oh, sorry. Oh my God. Okay. Okay, yes, I'll just start over. Right, so I will be highlighting the waste treatment section of the presentation. So essentially, control strategies optimizes disposal costs and resources while minimizing impact to the environment. Hence, the proposed methodology for this section is by identifying and analyzing the pollutants first with regards to the regulatory limits and standards alongside the relevant control strategies. So as for the waste identification, we divided it into the phases. For the solid phase, we have the molecular sieves in form of spent adsorbents from the dehydration unit, mineral scales from the utilities of the system, and thirdly, mercury in the form of spent adsorbents from the MRU unit. Secondly, we have the liquid waste in the form of sludge and produced water from the separators and spent solvent DEA from the AGRU unit. And thirdly, we have the sour gas streams from the absorption and stripping unit. There are three regulations to consider. Firstly, the environmental quality in accordance to the industrial effluents. It emphasizes standard A and standard B being assigned to the upstream and downstream water intake correspondingly. So for instance, suspended solids should be within the catchment of 50 milligrams per liter and standard B should be within the catchment of 100 milligrams per liter. Second is the environmental quality for scheduled wastes. So here the spent solvents, sulfur and mercury are to adhere limits which is stated in the 4th and 1st schedule of regulation number 2. And thirdly is the environmental quality for clean air. Here we have mercury and hydrogen sulfide to adhere to the respective limit values, and it's monitored periodically. So I will be presenting on the solid waste firstly. So scale deposits are form of major waste since the cooling water and raw natural water consists of magnesium and calcium traces. So the scales here are crucial to be removed to minimize fluctuation of heat transfer rates. And then the system functions by pumping cleaning balls into the tubes to remove the hard scale deposits, which will then flow out in the cooling water washout. The stream will then flow to the wastewater unit for further treatment. And the collected balls will be recirculated back into the system. I will then pass on to Amrila to continue the presentation.
Okay. I'm Amrila. I will continue for the solid waste treatment of spent adsorbent in MRU process unit. So generally, there are three types of technology for mercury waste treatment, including stabilization, vitrification, and thermal treatment. Among all of the technologies, thermal treatment process was chosen as it is identified to be the most applicable for FLNG plant due to its simplicity of process operation. Thermal treatment is defined as a process that utilizes the heat under reduced pressure to completely volatilize the mercury on spent adsorbent. So as this process performed under reduced pressure as well as vacuum conditions, so it has the this process reduces a significant amount of energy cost as well as the gas emission. This process also possesses the highest removal efficiency of mercury from spent adsorbent, which is around 96%. So there are three main sub-processes under thermal treatment process, which is the pre-treatment, desorption, and also post-treatment. For the pre-treatment, all of the contaminated waste on spent adsorbent will be removed in order to achieve a suitable moisture prior to the treatment process. Then in desorption process, the spent adsorbent is placed into thermal desorber to undergo the heating process up to 700 degrees Celsius. After that, in post-treatment, the volatilized gas mercury will flow into wet scrubber in order to obtain clean of gas before it being condensed and finally being stored in a permanent storage tank as the scheduled waste. Moving on to liquid waste. So the source of water is basically come from our phase separator, which is the produced water, spent solvent, and also the washed down water from utilities. So for our FLNG plant, we only consider up to secondary waste treatment process due to space constraint. And on top of that, at the end of this process, at the end of the secondary process, we already produce a wastewater that comply with the regulation as mentioned earlier. So In primary process, mechanical bulk screen is used to remove around 20 to 35% of total solid, which then continue flowing into the mixing tank, where the sludge form into bulks due to coagulation and coagulation and flocculation process. Then this wastewater will flows into aeration tank, DAF tank, where the suspended solid will be floated into the surface due to the formation of the bubble in that processing tower itself. Then only the sludge will be skimmed off. So the wastewater we further flow into secondary process, which is the biological treatment, where the content of BOD and COD of the sludge will be reduced. After that, it will further transfer into secondary clarifier and being discharged. So I pass to the next presenter.
Thank you, Arms. I will now continue with the gas waste. So as for the gas waste, sour gas is our identified waste. Carbon dioxide from the sour gas will be vented into the atmosphere. However, sulfur is required to be treated or recovered due to strict regulations, as well as possibly upsetting the downstream processes. So the selected treatment is the liquid redox, as compared to the close process, as the H2S concentration in our plant is below the 15% percentile. So as we're producing only 0.157 concentration. So supposedly after treatment is minimized further and will adhere to the limit of 7.5 concentration, which is in compliant to the third regulation as mentioned earlier. So in this system, the iron is used as catalyst to oxidize the H2S and form elemental sulfur from the gas streams and will be regenerated and used again. So that is all for our waste treatment. We'll pass on to the next presenter.
All right, thank you, Jasmine. My name is Afiq. I'll proceed with the cost estimation of the plan. So this is the list of aspects that we have considered and calculate to determine the profitability of the plan. So for the evaluation of the project economics, so this is to approximate the value of the entire project, such as incomes and also expenses from starting until the ending of the plan lifespan. So what we have calculated are depreciation, cumulative cash flow, rate of return, payback period, and also net present worth. And there are some parameters that we need to use in order to determine the cost analysis of the plan, such as the plan lifespan, which is 15 years, operation per year 340 days excluding the maintenance, construction period 3 years, and also the minimum rate of return, which is 15%. All right, for the economic potential, basically this is to provide estimation of the profits generated by the plan. So after we have calculated the EP1, EP2, and EP3, which is the summation of product plus byproducts minus the raw materials, utilities, and also the annualized manufacturing costs, we still have a huge amount of profit generated by the plan. So this amount will ensure the sustainability of the plant operation throughout its lifespan. So this is the OPEX and the CAPEX, which is the operating expenses and also the capital expenses. So basically for the OPEX, it can be divided into two parts, which is direct cost and also indirect cost. So for the direct cost, on the left hand side, we can see the amount of the direct cost is 55 million ringgit and the indirect cost is 21 million. So the total OPEX for this plant, which is the operating expenses, which is 76 million per year. So for the capex, which is the initial investment, is around 467 million ringgit. All right, for the breakdown of the total capital investment, which is the capex, but as I mentioned just now, it can be divided into 3 years, which is for the first year is 25%, which is designated for the designing and also engineering, 65% for the second year, which is construction and procurement, and the third year is 10% for the remaining construction, and the total is as I mentioned just now, like the capex, which is 467 million ringgit. All right, for the depreciation, for everything that have been constructed, the value of the properties will be decreased over time. So this is the formula of the depreciation, and after we have computed the necessary parameters in the equation, and we have obtained the depreciation value of 30 million. So this is the value, the amount that will depreciate the plant every year. So for the cumulative cash flow, so this is the transaction of money from the beginning of the plant construction until the end of the plant life. So basically, as you can see on the most right hand side here, the right column, you can see the first 3 years is the capex, which is the initial investment, where we can see the negative value, and until the third year it becomes the positive value because we start getting the profit from the plant operation, and until the 50th year, which is the final year of the plant lifespan, we are able to obtain about 2,600,000,000 ringgit Malaysia cumulative net cash flow. And for the rate of return, this is to determine the feasibility of the investment toward the plant, whether this plant will gain profit or loss throughout its lifespan. So this is the formula that we have utilized when calculating the rate of return, and the value that we have obtained for the ROR is about 37.2, which is exceed the value of the MARR, which is minimum rate of return of 15%, which indicates this plant is very feasible for the investment to be made, and will ensure the sustainability and also the profitability of the plant throughout its operation. Alright, for the payback period, this is to evaluate the number of years required by the plant to obtain the break-even, which means the investment that we have made is equal to the amount of incomes from the sales. So as we can see in the graph here, which is the figure here, we can see the second year is on the line where this is the break-even year, where in the second year itself, the break-even can be achieved where the investment is equal to the incomes, and starting the third year, which is the third year until the final year, which is 15th year, we are keep getting the profit until the end of the plant lifespan. Alright, so for the next net present worth, so basically the positive net present worth indicates the plant is generating higher income compared to expenses during the plant operation. So the left hand side is the equation of the net present worth, and the right hand side is what we have calculated using Excel. So as you can see, until the end of the plant lifespan, which is the 50th year, we can obtain the positive net present worth when considering the MARR, which is 15%, and this indicates the plant is generating a lot of income and can overcome the amount of expenses, which means this plant is sustainable to be for the operation of to produce the desired product that we want to sell. So with this, I'll pass to Rashwinder to proceed with the individual equipment design.
Thank you, Afiq. So the major equipment that I selected was the separator, the flash separator. So I'll start up with the operating conditions. As it can be seen here, the operating temperature is about 70 degrees Celsius, the pressure is about 70 bar, and the other important specifications included are the inlet flow rate, vapor flow rate, liquid flow rate, the liquid density, and gas density. Now I'll move on with the basis of selection. So basically the basis of selection was done based on the feed content, where the feed was mainly liquid and gas. Therefore, a two-phase separator was suggested instead of a three-phase, as there was no oil present. Now I'll move on to the process sizing methodology. So firstly, calculate the vertical terminal vapor velocity, which is actually the maximum permitted vapor velocity in the separator. Then the inside vessel diameter has to be calculated using some values from the simulation. Then the hold up volume and hold up time, search volume and search time are also calculated based on the table provided in the report. Then the low liquid level height value is also gotten from the table provided in the report. After that, the hold up height and search height are also calculated using some equations. After that, the height from high liquid level height to the center line, which is the inlet nozzle or the feed, is also calculated. Then the disengagement height from the center line to the demister pad is also calculated as well. Lastly, the height of demister pad in the total height is calculated. However, one of the most important thing in the whole process sizing methodology is checking the LD ratio or length to diameter ratio. Now moving on to the selection of criteria. Can you guys see my slide is lagging?
It's okay, take your time.
Oh, sorry guys, my slide I can't see. Okay, never mind, I'll open on. Okay, so can you guys see my slide? 1 minute, guys. What is?
We can see your slide, Rashminda. Is it process sizing methodology?
Yes. Is it selection criteria there? I'll just talk based on what I know.
Basis of selection, yes.
Okay. Is it can someone take charge and let me present, because my
I'll take. All right, now it's process sizing methodology.
Selection criteria, is it?
Yes.
Okay. So basically, as you can see here, the vapor disengagement diameter, or the diameter of the vessel, is about 0.978 meters, and the miseliminator or demister pad was added. So therefore, 6 inches was added to the vessel, which made about the total vessel diameter about 1.130 meters. So according to the process sizing methodology just now, all the heights were added in order to get the total height, which was about 5.354 meters. And then the LD ratio gave about 4.74, which proves the calculation as the range falls between 3 to 5, which is the perfect range for a vertical separator. Any range above than 5 is for horizontal separator. Now moving on to the next slide. So in the next slide, as can be seen here, this is the mechanical sizing methodology, and these are some of the important mechanical specifications, where the material of construction is the stainless steel type 304 instead of the carbon steel, because carbon steel is cheap but not as strong as the stainless steel type 304. So stainless steel was chosen as it can withstand high pressure. Another important thing here is the design of head or closure, where the toruspherical head was chosen instead of the hemispherical head, even though the hemispherical head could withstand higher pressures, because the material of construction is already good enough to withstand the pressure. Some of the important specifications are the feed nozzle sizing, vapor nozzle sizing, and the liquid nozzle sizing. As you can be seen here, this is the mechanical sizing methodology. Now moving on to the next slide. So this is the specification sheet, where the operating conditions, pressure, temperature, then the diameter, height, and the flow rates are included, and it's proven that all the specifications fit perfectly for the vertical flash separator. Now moving on to the next slide. Okay, as you can be seen here, this is the mechanical drawing, where high liquid level height and low liquid level height is perfectly created there to show the dimensions. And then it can be seen here that HT represents the total height of the separator, and then there's HME, which is the height from the demister pad to the closure, and then there is also HD, which is the disengagement height from the inlet feed of the nozzle to the demister pad, and there's HLIN, which is the height from the high liquid level height to the inlet nozzle. So these are some of the important parameters of the drawing. And then moving on to the toruspherical head, where the parameters include crown radius was calculated, knuckle radius, thickness, and also the height of the toruspherical head. Now lastly, there is the circumference of the diameter, where it can be seen here the internal diameter is about 1.13 meters and the outer diameter is about 1.137 meters. That's all for my part. Now I'd like to pass it to the next person to present. Thank you.
Is that muted?
Okay, for my major equipment is the absorption column. So the design methodology for the absorption column is design operating parameters, material selection and specification, process design of absorber, wall thickness determination, selection of head and closure type, gasket, bolts and closure design, determine combined loading, stress analysis, skirt support design, and lastly nozzle sizing. So the basis of selection, according to following equipment specified in chemical engineering textbook RKC 2005, carbon steel is selected as building material because it's very lightweight. Maximum allowable stress up to 135 Newton per millimeter squared at 0 to 50 degrees Celsius, and it also corrosive resistance toward CO2, H2S, and other sulfur organic content. 3-inch racing rings ceramic is selected as packing material, only applicable with a pressure drop greater than 42 kN per meter squared. Groove metal is selected as gasket material, enough to withstand minimum design seating stress, and also the gasket width design is more than minimum required gasket width. And lastly, carbon steel is selected as board material, which maximum allowable stress up to 159 Newton per millimeter squared at 0 to 50 degrees Celsius. So these are the sample calculation for the column design, column diameter. Using the equation for the gas mass flow rate per unit column cross-sectional area, you get 19.1 kg per meter squared second. And then using the column area equation, which is gas mass flow rate per unit column cross-sectional area, this gas mass flow rate is in kilogram per second. We get 3.6 meter squared, and for the diameter we get 2.14 meter. So for the column height, using this equation, we get a total height which is approximately at 27 meters. And then for the number of stage, by using the reference of the correlation graph, we get the number of stages at 20. So these are the specification sheet for the absorption column. So the important parameter is such as operating pressure at 70 bar, and also the operating temperature at 35 degrees Celsius. So the total dead weight, the bottom of the table, at 689 kilonewton. So these are the other specification, which for the packing specification, both flange and skirt parameter, and also the nozzle sizing. For the drawing of the equipment, you can see the total height is the height of the absorber is 27, the skirt height at 22 meter, and also shown is the size of the nozzle for the inlet gas at 491 millimeter, the inlet of the solvent at 341 millimeter, for the liquid outlet at 352 millimeter, and also the gas outlet at 463 millimeter. For the diameter of the inner diameter of the column is 2.1 meter. Outer diameter is at 2.16 meter, and also the diameter including the insulation at 2.17 meter. So I pass to the next presenter.
Your mic.
Jasmine, muted.
Sorry again. So I'll be presenting on the divided wall column. It's used to separate the three products, with methane as the top, ethane as the side stream, and propane as the bottom stream product. So the column employs the similar vapor liquid contact just as the conventional distillation column. However, the concept of the DWC is to reduce the number of fractionation trains, such as demethanizer and deethanizer, into a single shell with the inclusion of a partition wall. So as the multi-component is being fed into the column, the quality of the methane is increased at the top, while propane is being increased at the bottom. Some of the advantages to take note is the reduction in utility and energy costing, as well as it being able to serve as a standalone unit with minimized compression. As for the design methodology, firstly, the level of separation was specified with regards to the product composition and the operating conditions of the distillation column. This is then followed by the calculation for the number of stages, the reflux requirements. This information is then carried forward for the column sizing, the dimensions, as well as the internal specifications. And lastly, the accumulated information is used for the mechanical design considerations. These are the operating parameters of the column, where the volatilities are taken into consideration with respect to the stage compositions of the light key and the heavy key components. The compositions are driven by the vapor pressure and is separated by their boiling point difference. these are some of the sample calculations I've included. So firstly, using the Fensky equation, the minimum number of stages was found with reference to the component volatilities as mentioned earlier, following which the minimum reflux was evaluated to find the actual reflux at 0.75. The plate efficiency is then evaluated using the correlation, which uses the average volatility again and the dynamic viscosity of the feed and is valued at approximately 62%. And finally, considering the ideal and the minimum number of stages, the actual number of stages was found at 33. Now, the feed point was evaluated at the 5th stage using the Kirkbride equation with respect to the rectifying and stripping stages. As for the column diameter, the cross-sectional area was taken and used to correlate with the equation of the circle. And then the height of the column is in relation to the number of trays. It uses the height to diameter ratio of 0.6, and the 15% extra is for the spacing, and the evaluated value is about 23 meters. Now, as for the number of holes in the tray, it was based on a theoretical value of the area against the actual hole area, with resulting about 14,000 holes. Another sample calculation included was the shell thickness, which includes the column diameter, the yield strength, as well as the design pressure, with an additional corrosion allowance of 2, and the final value is about 21 millimeters, 21.6 millimeters. This is my specification sheet containing the stream conditions and the mechanical design. So as for the material of the vessel and the supports, for the column I've chosen was stainless steel. And an aspect of the mechanical design for the nozzle thickness for the feed is more than the vapor and liquid, as they were based on the mass flow rate and the mass density of the compositions. So, this is my technical drawing, which shows an overview of the cross-section of the column with the respective nozzle thickness and height of the column as mentioned in the specification sheet and the earlier parts. So, the head closure chosen was ellipsoidal as compared to tori spherical. As for the cross-section of the sieve tray, it consists of the wear length and the inner and outer diameter gasket at approximately 2.6 millimeters. As for the hydrodynamics and the holes layout, both of them highlight the diameter of the hole at 0.005 meter and the plate spacing at 0.6 meters. So that is all from my part. I will now pass on to the next presenter to present their part.
Okay, for individual equipment, I have designed the dehydration column C203. So this dehydration column utilizes the adsorption process by using molecular sieve. So for the process design methodology, it is started with the selection of adsorption column in terms of process operation, obtaining inlet and outlet stream data together with parameter of adsorbent. Then the water content in dehydration unit is determined before calculating the amount of water to be removed. This process design continued with the calculation of pressure drop, diameter column, amount of absorbent required, length of bed at saturation zone, and length of mass transfer zone, total bed height, and also total vessel height. So for the basis of selection, the operation of adsorption process is chosen to be continuous rather than batch process, because continuous process led to ease of operation, faster the absorption process due to reduction of processing time, and also possess a simplicity of scale-up process. The other basis of selection would be the type of adsorbent used. For this dehydration column, molecular sieve is selected as it possesses the higher purification ratio compared to zeolite, has a large and uniform pore size to ensure higher removal of water molecules. And lastly, it may reduce the operating cost as this type of adsorbent can be regenerated. Okay, moving on to the sample calculation. All of the parameters highlighted in process design methodology are presented with detailed calculation in this session. So as we can see here that The amount of water removed in dehydration unit is approximately to 4.5 kg per day, while for the column design, the inner diameter is around 2.3 meter with a total bed height of 7 meter and also the total length of vessel 7.6 meter. And the pressure drop inside this dehydration column is expected to be 5 kilopascal. So this is my specification sheet. It is included with operating condition for each of the stream data along with the mechanical design. For the mechanical design, the type of material selected is stainless steel for most of the equipment part, including the vessel, nozzle, and gasket. This is because stainless steel seems to be the most economical among the other material, and it also able to resist the corrosion that may caused by the working fluid itself in the absorption column. So these aspects are very crucial for our FLNG plant because we want to optimize the operating costs, especially on the equipment costs, but at the same time we are targeting the most efficient process. So for the mechanical design, here is the detailed drawing of my dehydration column. So as stated earlier, the length of the total column height is the 7.6 meter, while the total bed height is 7 meter. So for the head closure, ellipsoidal design has been selected as it is commonly used for the system with the operating pressure of higher than 15 bar, and it also has a cheaper cost compared to hemispherical and provide a lesser internal volume. So apart from that, for the gasket, it is designed, the inner diameter of gasket is designed with a 10 millimeter larger than the outer of the column. So for the skirt support, I choose a conical type rather than straight circuit support with a height of 1.8 meter in order to achieve high stability on our FLNG facility by considering the motion effect that caused by the sea waves as well as the effect of the wing loading itself. So that's all for my part. I pass to next presenter. Thank you.
All right, thank you, Amrila. My name is Hafiz, so I'll proceed with my major equipment, which is distillation column C202. So for the design methodology, this is the aspects that I have considered when doing the calculation for the distillation column, such as material selection, design operating parameter, process design, number of stages, reflux ratio, thread efficiency, feed tray location, height of tower, internal column sizing, and last but not least is cost of equipment. Alright, so for the type of distillation column, I have chosen tray column instead of a PET column because the main reason here is it can tray column can handle wide range of gas and liquid flow rates compared to PET column, and other advantages such as accuracy of the plate efficiency can be predicted, operation of the plate column is smooth, provide stage-wise contact in the tray column, and last but not least is the easy to clean the tray when during maintenance if there is any deposition of solids or fouling. All right, so for the
sorry to disturb, Mr. Apik. So, Dr. Linda and Dr. Nick, can you see the presentation? Can you see the screen?
Yep.
Yeah, it's okay because I cannot see the screen. It's only the white background. Okay, if you can see, I think it's okay. Apik, you can proceed. Thank you.
Thank you. So for the sample calculations, here are the few calculations that I have evaluated for the distillation column, such as the first one is minimum number of stages, which is around 2 stages, minimum reflux ratio, which is 0.13, actual reflux ratio 0.19, tray efficiency, which is about 67%, the actual number of stages, which is 11 stages or trays, feed tray location, which is at the 8th stage, and the tower height estimation around 12.8 meter, and the column diameter is about 1.38 meter. Alright, so this is the specification sheet for my distillation column. As you can see, it consists of the operating data, internal condition, and also technical and mechanical specification. From here, you can see the all the calculations that I've input based on the report. And for the details calculation, you may refer the report. And here I want to highlight a few parameters such as the materials, such as for the column is we'll use the stainless steel, and for the installation is mineral wool. So I'll proceed with the equipment design. So this is the drawing that I've made. So the first one is the column itself, where the height is about 12.8 meter on the left hand side here, and the skirt height is around 0.31 meter, and the skirt thickness is 10 millimeter. And below here is the foundation of the column, and in the middle here is the shell thickness, the shell itself, which is 10 millimeter, and the distance between two trays is about 0.5 meter. And the last one is the tray dimension, where the inner diameter is about 0.35 meter and the outer diameter is 0.5 meter. So the thickness is about 50 millimeter. So with this, I end our group presentation and we'll proceed to Q&A session. All right, sir. Dr. Haslinda and Dr. Hadi, is there any questions?
Okay, so this is the last slide.
Yes.
How much time we have left? So 20 minutes. Let's go to the waste part. So let's focus on the PDP2 punya section only.
Okay. Jasmine, can you take to control?
All right. Okay. So which part of the waste?
Can you go to the slide? I think better slide berapa ya?
The solid waste, the gas waste, or
better liquid waste first.
all right.
Liquid waste first.
There you go.
Slide 17. Yep, this one. Okay, can you tell me what is your wastewater coming from? Dalam you punya wastewater ada apa?
We've got three sources of the wastewater.
Okay.
They're from the utilities, the washdown, boiler washdown, and then we have the produced water from the separator, the sludge separator, and then the spent solvents. Yeah.
Okay, so komponen dalam wastewater tu apa yang you expect ada dalam tu?
The composition, you mean, sir?
Yeah.
You mean the concentration amount?
Not concentration, just component je dalam you punya wastewater.
Okay. So there were. Okay. They're like. So basically, from before the preliminary, before it gets treated, there's like scale deposits. There's the solvent, the spent solvent, and then the balance produced what? It has like oil deposits.
Oil deposit, okay.
Yeah.
So which part does oil being treated here?
There's no treatment of the oil. It just gets, it's part of the sludge. So from the sludge separator, it just gets carried forward to the wastewater unit.
I don't understand. So yang masuk dalam wastewater kat sini adalah containing water, oil, MDEA.
Yep.
Okay. Yep. So
they're from separate streams being connected.
Yeah. From this one, kat mana yang akan remove oil?
Okay. It's from the preliminary and the primary. So it's like a specialized bar screen.
Specialized bar screen tu apa maksud dia?
It's supposed, because oil is part of total solids, so the total solids essentially gets removed.
Okay, so itu untuk oil yang tak emulsified dalam water. What about oil yang emulsified?
it gets treated in the mixing tank, the coagulant and the flocculant. So when coagulant is added, and then like there'll be like a skimming process. So the oil droplets will get attached to the coagulant and flocculation, and they float up to the surface, the DEF, and a skimmer will skim off the waste at the top. And that is either kept in a storage tank, or it's most likely kept in a storage tank rather than being disposed out in the water mediums.
And what about MDEA? Bahagian mana yang dia akan treat for this one?
MDEA essentially, it's from the coagulant as well, right up to the biological tower. Whereas aerobic processes, there's like microbes being added inside the tower, and there are the aerobic digestion there sort of reduces the concentration, the hazardous alkalinity level, so that it is safe to be disposed out into the water medium. We're not keeping the spent solvents for regeneration because it's already spent. So that treatment somehow because you don't because this is it's a proposed methodology, sir. So
your proposed methodology, proposed methodology should tackle what is in your wastewater.
Okay, sir.
So itu the concern actually.
Okay.
For the gas H2S,
yes.
How was it treated guna biological? Liquid redox.
All right, yeah, the liquid redox. Meaning, how does it work, sir?
Liquid redox, berapa banyak H2S in your acid gas?
Okay,
and,
in our acid gas, we have about 0.157 milligram per meter cube of H2S. Okay. So, which is below the 15. If you see that there's a fraction diagram there. So essentially, we'd want to recover sulfur instead of carbon dioxide being released into the atmosphere, because it has due to strict regulations, and it upsets more.
So this one CO2 tak treated.
CO2 is vented into the atmosphere.
Okay.
Yeah. Okay. It's because of the regulation limits, and it's mostly because of the regulation limits. That's why we can choose to release instead of, because there was an option to reuse the carbon dioxide and re-inject it. There's a system for that. But if you were to consider that, then that would incur other cost factors as well.
Okay, we still have a few minutes left. Can we go to the sizing? Let's look at the flash separator first. Better let's go to the slide 34.
Rashwin, do you want to take over?
Is this slide 34?
Yes, sir.
Lain dengan you bagi kat kita orang. Okay, next slide.
Oh, okay. Alright.
Mana si Rashwin tu?
Rashwin?
Rash, you there?
Sir? Yes, sir.
What is the volume of your flash separator?
The volume is sir.
Sekejap je. Okay, cuba you kira dulu. $1.13.
The hold up volume was 2.33 meter cube.
Your flash punya volume is 5.4 meter cube.
Yes.
5.4 meter cube. Liquid hold up berapa meter cube?
Liquid hold up was 2.32.
2.32 meter cube. Gas hold up?
2.33 meter cube, yes.
Gas hold up?
Hold up volume. Yes.
Gas hold up?
Gas hold up is the rest of the thing. Only the liquid was calculated.
Okay.
That the gas fills up the rest of the thing. So I'm only focusing on the hold up volume of the liquid.
Wait,
Hello?
Yep. 953 meter cube per hour, so 0.19. Okay. Flash separator ni dekat mana?
Is right in front, depan, paling depan at the P&ID diagram, in front of the process.
Okay, I don't understand that. So
No,
masuk
it's the first
initially
unit.
terus
It's the
masuk
first unit
flash
in the
separator.
FLNG. Well, yes. Pardon, sir?
Sekejap, I try to find your P&ID. Kat mana flash? The first one is phase separator.
That's our flash separator, sir.
So itu flash separator?
Yeah,
Okay.
it's a two-phase separator.
Two-phase separator, okay. Sekejap, I cuba get back to this slide. So design pressure is 2630 bar. Liquid outlet, kenapa liquid outlet flow 70 meter cube per hour?
You are seeing my report, is it, sir?
No. Same slide. On the specification sheet, your liquid outlet flow is 70 meter cube per hour.
Yes.
Kenapa berapa
That's
banyak
the liquid
liquid
flow rate, sir.
dalam your inlet liquid 70 meter cube per hour?
No, actually the liquid is very less.
So why the liquid outlet flow 70 meter cube per hour?
Because if
Macam
it's
ni
too
dapat
high,
70 meter cube ini?
because in the design specification, if it's too high, then the calculation will also go wrong, sir. Cannot be too high. Because the gas flow rate is always faster than the liquid.
Okay. So the question is, how does you get 70 meter cube per hour for liquid outlet flow?
From the simulation, sir?
How does you get the value of liquid outlet flow of 70 meter cube per hour?
From the HAZOP, sir.
From the HAZOP. I don't think it's this high.
It's too high, sir?
Berapa banyak dalam you punya case study, you punya problem statement, berapa banyak ada liquid?
It's about, wait, 1 minute, sir. Yeah, so the water, it just says normally gas from reservoir is saturated with water. So we assumed it was very less, about just 1% like that.
Why do you assume 1%?
Yes, sir. What is it?
Why 1%?
Because it says saturated with water, so we assume it's not that much. Therefore, we was just using flash separator instead of a normal two-phase separator.
They have their own certain value for saturated, right?
I'm not sure about that, sir.
I am very sure that they have a specific value when it is saturated.
Because in our question here, it was not given the percentage.
Because it gave you saturation. Saturation, it's in saturated. Okay, let's move on dulu. If you cannot justify this, let's move on first. Absorption column C201. Mana specification? Slide 42. Slide, yeah, this one. This one is to remove. This one is for AGRU, right?
Yeah.
So AGRU. Mana diameter? Diameter 2.14. Diameter 2.14. The height is 27. Okay. Ini guna amin tu tadi ya?
Yeah. DA.
2.14, 27. So your volume of your column is somewhere around 97 meter cube. So berapa banyak you punya masuk, berapa banyak solvent masuk dalam ni?
Solvent is 852,000 kilogram per hour.
Berapa?
52,000
852,000
kilogram per hour.
kilogram per hour. Dalam volume? In terms of volume?
Mm.
236 kilogram per second. This is your solvent use. Okay. So volume dia berapa ni?
800 meter cube per hour.
800 meter cube per hour. Kalau per second? So 0.22.
0.2.
Lepas tu gas volume dalam tu adalah? Messed up.
Is around 693
Unit
meter cube per hour.
per second?
Zero point one nine
0.19 meter cube per second gas. So liquid adalah 0.22 meter cube per second. Okay, itu sounds logic. Let's move on to the next one, which is, do we still have time? The next one is divided wall column. Ini slide apa? Slide 50. Okay. So temperature feed is 63. Top negative 1 to 3. Side 99. Bottom 73. Diameter of this one 1.55. The height kat mana height dia?
Height is under the technical and mechanical data, sir.
Oh, 23 tu.
Yep.
23. Tray spacing.
Tray spacing is not specified here, but it's an assumed value of 0.6.
0.6 meter.
I've mentioned it's in the spec drawing. Highlighted it there.
You punya inlet, kalau you tengok the technical drawing, the feed masuk dekat mana? Technical drawing.
The feed enters at the 5th stage.
The 5th. Next slide. Next slide.
Oh, okay. I take control. Right. Do you see it, sir?
Okay, can you highlight pointer? Which one feed?
How do I point? Am I pointing?
Nope. Tak ada.
How do I?
This mode cannot have pointer.
Okay.
Okay. Yang masuk tu yang sebelah kanan kolom ke kiri kolom?
At the left side, sir.
At the left side, okay. Because top you mentioned negative 100 something. Yang masuk adalah 60 something. Inlet temperature negative 63.
Yes.
Top is negative 123.
Yes.
And bottom is negative 73.
Yes.
So your temperature profile macam pelik je. Ada berapa stage this one?
There's 33 stages.
23 stages.
33 stages.
33.
Yes. Tray from top to bottom is 33 stages.
Yeah, it's not right, right? The temperature profile is not right.
Bukan yang bottom sepatutnya
Bottom
lagi
sepatutnya higher.
higher. I wonder how.
You're separating methane from the rest. So what is the temperature of those other things, right? C1. So C1 has the lowest boiling point. Am I right?
Yes.
So the bottom should be of higher temperature because they are heavier.
So, yeah, betul.
Okay.
Check balik.
It's
Ini tak kena. If you try to plot y-axis is stages and x-axis is temperature, you try to plot. Kalau dia somehow bagi you weird curve, itu something wrong lah tu.
I guess Dr. Hadi, the principle is still the same, right? Whether you divided wall column or you just use simple distillation column, the key separation is due to the temperature difference, right? Yeah, so you go back, Jasmine, to your basic distillation column knowledge.
okay.
How do we separate? We always have light key at the top and heavy key at the bottom, right? And they are separated due to their different boiling points. So this one is not, I think it's not following that rules. You need to check.
Okay, doctor.
Mr. Aker already get angry. But let's go the last one, dehydration unit. Dehydration unit, slide 54. Slide 54 just tells me the volume of your bed.
My volume is 30 meter cube.
30 meter cube. Volume of apa tu?
Volume of bed. No, volume of vessel is 32.7 meter cube.
2.7. Can you show the specification?
Sure.
Data sheet tu.
Stick control.
Yeah. Okay. That is lagging.
Oh, tak keluar lagi.
No.
So inner diameter is 2.33.
Yeah,
The height
2.33.
is
Oh,
kat mana height dia?
my height is for bed is 7.06.
7.06.
Yeah.
That will make your volume is somewhere around 30 meter cube.
Yeah, 30 meter cube for the absorbent, but for the total height of the vessel is 7.6. So the volume of the vessel is 32.7.
Okay. 32.7. Okay, seems logical. Pressure drop. Tadi you dah calculate kan pressure drop?
Yeah, pressure drop is 5 kilopascal.
Ini untuk mercury tadi
This one is for dehydration column.
Oh, dehydration.
Yeah.
Okay, seems logic. We are over time. Supposedly siapa last kali tu?
Afiq.
Entah Pak Afiq, I will judge based on your report.
Right, sure, sir.
Okay. Thank you, Group 3.
All right.
You've
Thank
done
you,
a
Dr.
good
Dick.
job.
Thank you, sir.
Good luck.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Dr. Dick. Thank you, Dr. Haslinda, for your time. So that's all from us.
Thank you. Bye-bye.